So we learned how to make them, which is awesome. Question first, yeah. There's always going to be lab time, yeah, for the stuff that's already out. Yeah. All right. So yeah, let's talk about functions some more. We learned how to make them. We'll learn how to test them using that assert true function. It was wonderful. You figured out some stuff. I just want to teach you some more details now. I want to teach you something called the stack, or the call stack, or the runtime stack, or the function call stack. There's a bunch of different names for it. I will usually just call it the stack. All right. So this will answer this little subsection of the lecture. We'll talk about like what happens when I call a function in C++. How does it like know? How does it know like from main I called like the square function or something? Like it sent control of the program to the square function off first for like a split second. And then square knew like to go back to that line underneath it in main, like that, now I'm done, right? How did it know how to get back to where it was? How does it know where it left off? All right, so yeah, let's draw a pretty picture using a stack diagram. All right, so every time a function gets called, we say it's pushed onto this thing called the stack. It's like a stack of like papers, all the work that needs to be done still. So the stack is where your program is remembering what to do. So the very first function that gets pushed on the stack is the main function. That's being called by like the terminal or somebody. And so here's like the ground. And then here I'm going to draw a rectangle, and that is the main function. It's going to represent the work that the main function needs to do. All right, so that's the stack of works and papers for the main function. And then every time you call a function, it's going to push that new stack of work onto the stack. Okay, it's perfect. And that's going to be exactly the way how functions know who to return back to. Because like the person below you on the stack is who you need to return back to. So like in our example from last time, we like main called like sum squares from 1 to 2. Let's call that sum. Main called sum. And so to draw kind of what's happening, and this is actually happening in memory secretly, main called like the sum function. All right. And then sum can look underneath it and notice, oh yeah, when I return, I need to go back to main. That's how it remembers. And then maybe sum, we're doing some work in the sum function, right? We're calling that square function too. Sum called the square function. And like, you can see the stack of work that needs to be done. Main is waiting on the sum function, who is waiting on the square function right now. That's kind of how you read that. All right. So that's what's going on. That's how you remember it. And this is actually the spot where all the local memory gets made for each function, in each rectangle for that function. These are called stack frames. The stack frame for main, the stack frame for sum, for square. And all the local memory gets made here. So I've been drawing like variables sitting out in the open, but secretly I should have been drawing them inside of the stack. All right, so main maybe has some like an x local variable, an a local variable, a b or whatever. All that memory for that function is part of its stack frame, we say. All the local memory lives there. And then maybe like sum, it has two things, right? You're summing two things up maybe, I don't know, a and b. They are different a's and b's, and you can see the difference now. It's part of the sum function. It's part of its memory, not the main function's memory, all right? And then square, it took like a parameter, took a thing, and it needed to save that, of course. It was just a special variable. And then, yeah, that's kind of how it works. And square knows to return back to sum knows to return back to main. And when you're done, like, it's always the person on top. That's the person that's doing the work right now, the person on the stack of work to do. When a function returns, like the metaphor is you push it onto the stack, and somehow like you pop it off of the stack, like it's a bubble, all right? So you pop it off the stack, and then like square returns back to sum. You kind of like erase that. You erase that, pretend I erased it. Now sum's at the top of the stack. That's the work that needs to be done. We're back in the sum function, okay? That's kind of the idea. And then sum does all its work, and sum has got an answer finally ready to return back to whoever called it. It knows that main called it. It's below it, all right? On this magical place called the stack, so it'll pop itself off the stack, give its answer back to main. Now we're running where we needed to run. All right, we're back in main now. All right, so that's very, I know, vague. I'll give you like a concrete example, and we'll draw stack diagrams today to make it make more sense. But yeah, this is a key piece. Like every function has its own local memory, and that is where local variables live. All right, I don't know if I've used that word too much. So let me show you the difference between local variables, and there's another kind called global variables, all right? You'll have to humor me because I'm a millennial. I'm going to use Harry Potter as an example of this because Harry Potter's like the boy who lived forever, right? So if you make a function, if you make a function, you make a variable inside of that function, it's called a local variable, right? Even in main, still a local variable, right? And then variables that you make outside of a function, I'm not sure if I've shown you that yet, it's called a global variable, right? So let me show you the difference, and I'm going to use Harry Potter as a silly example. So Harry is the boy who lived. He's going to be a global variable, right? He's going to live forever for the life of the program. And spoiler alert, this dude, his name is Cedric. Unfortunately, he dies, and that is going to model local variables. Local variables, they lose their life the second your function returns. All that memory goes away. It's like you erase it. All these things are getting erased, all right? So here's my silly example, and then I'll draw a stack diagram, all right? Local versus global.cdp. All right, so yeah, let's have it like this. Let's make a variable outside of any function, just sitting out here. Call it an int Harry Potter, all right, equals 42. And so this is a global variable. It lives outside of any function. This is a global variable. It lives for the life of the program. Because you're not sure, like it lives forever, because you're not sure which function might need it, right? It needs to live forever, obviously. So that's that one. And then let's make a function, a new function, called Goblet of Fire, because that's the book where all this bad stuff happens to that dude. Goblet of Fire, and that'll just be a simple void function. I don't want to do too fancy of things. Void Goblet of Fire. And that's where I'm going to make another variable called Cedric, because that's the boy who did not live in that book, sadly. So Cedric, I don't know, we'll start him off holding some number, all right? And this is a local variable, just like if you made a variable in main, any function that you make inside of a function, or sorry, any variable that you make inside of a function is a local variable, all right? It's a local variable. It lives only as long as the function lives. So once the function returns, all of its memory goes away, gets reclaimed, so that you can call it again later and you don't like run out of memory. All right. So you can mess with Cedric all you want in this function. Cedric exists, right? You can say Cedric plus plus. You can see out Cedric, and then Harry, because he's global, lives forever, and you can use him wherever you want. You can be like, all right, Harry Potter plus plus. See out Harry. He lives forever. You can use him wherever you want. He's alive throughout the entire program. All right. And so I call a Goblet of Fire. We jump up here. We run all this code. We make a Cedric variable. But the second we return, Cedric dies, and so we can't access Cedric down here. All right. It won't work. You can access Harry all you want. You can be like Harry Potter plus plus again. Print him out. All right. But Cedric, you try to mess with him or ask about him, he does not exist down here. Right? It won't even compile, right? Because he was a local variable, he lived up here, if that makes sense. All right, let me do my best to show you both of these at once. There. So yeah, Cedric, sadly, Cedric is already dead right here. Sad face, all right? That's the idea, and this won't compile because of that line. And it's like, Cedric was not declared in this scope, all right? That's what it's saying right there. This variable does not exist. And so, yeah, the idea of a scope is like the lifetime of a variable. How long does it live, right? So Cedric is out of scope by here, we say, okay? Does not exist. I have to comment this out if I want this to run at all. Boop. And so here's the code. Let's watch it. Like it runs now. Let's see why it runs. So 94344. Let's see why. So the very first thing we do in main is call Goblet of Fire. And then we jump up here. Cedric is 8. Make him 9. Print 9. Harry Potter was 42 because he started out 42. Make him 43. Print him. Then this returns. We're back here. Make Harry Potter 44. Print that. Right? So that's the code. That's why it's working. Let me draw a diagram. Let me draw a stack diagram now for what's going on. Right? So like I said, all local variables, they live in the stack, on the function call stack. Every global variable is not part of the stack, right? So there's like a separate spot. But here's main. Here's main. We call it, main is the very first thing, start of the program. We push that work onto our stack. And then over here, like there's a globals section of memory for all your global variables. They're not part of any local thing, right? We made Harry Potter. That was the very first thing we did up here. So like when the program starts, all your global variables get made. Because you could use them at any time. Right, so that's 42. And then main called goblet of fire right there. And so we jump up here, we push the work that we need to do onto the stack. We're calling the goblet of fire function. Boop. We know to return back to main when we're done. All right. And so we make a local variable inside of goblet of fire. We say in Cedric equals 8. So we do that. That's what happens. Cedric is a local variable holding 8. We make him 9. Print him. So that's why we see 9 printed out. There's like the screen 9. And then we say Harry Potter plus print Harry Potter. So make him 43. Print him. He exists anywhere. He lives for the life of the program. Boy who lived. And then we're done. We're done with Goblet of Fire. That's the end of the line. We return back to whoever called us. We pop ourselves off the stack. All our memory goes away. Pretend I erased that. And now we're back in just main, where only Harry Potter is the only variable we could ever use right now. All right? It's the only thing that exists. So we can ask about him. Harry Potter plus, make him 44, print 44 to the screen. But if you ask about Cedric, again, he is part of a stack frame that is no longer in scope. All right? He's no longer in scope. The only things you can do is stuff from here or from here. There's no Cedric, right? So, yeah, that's kind of the idea. Does that make sense? Any questions about that?
So the function ends up disappearing?
Yeah, all the memory associated with that function because it's done working. There's nothing left to do. Yeah. And the idea is, imagine if it didn't, right? If you called Goblet of Fire like a million times in a loop and it never got rid of that Cedric memory, it would make like a million different Cedrics because he called it a million different times, and that would run out of memory in your program. So that's why it all goes away.
So you can only call a function once
No, that's not what I'm saying. I'm saying that you can call a function as many times as you want, and once that function returns, its memory goes away. So you can potentially call it again and not run out of memory. Okay. Any questions? Good thoughts. All right, so this is a stray slide that I don't need this time, and let's talk about a different concept if we're ready. All right, so that's the stack. That's should be in the back of your mind now, where memory lives. I want to talk about a different kind of variable now. It's called a reference. All right, it's kind of fancy. It's not real. It's kind of virtual in a sense. So I'm going to teach you some cool things. So I'm going to answer these questions. How do I modify the values that I pass to a function? One thing that you don't really know the answer to, you pass along an x, how do you modify it? How does that work? And also, how do I return multiple values at once? How could I possibly do that? Because you know that if you call something like square roots, for example, square root of x, that will return to you the square root of x and nothing more, right? I guess you could return a vector, that would work. That's one way to return multiple things. But what if you want to return like an int and a string at the same time? I need to show that to you, right? Can't do that with a vector even. And then if you want to modify values that you pass to a function, that's another thing you're not sure how to do yet. There's one function that you know that does that, by the way. It's called getLine, right? GetLine messes with the variable that you give to it. Usually it's just using that value, right? But getLine, you give it cn, and then you give it a variable, and it will fill in that variable when you call it, right? That's different. That's something we don't know how to do yet. So references give us that ability. It's one way to do it. It's the easiest way, right? So a reference is special, all right? It's not really a variable. It's an alias. It's just like a code name, a spy name for a different variable, all right? So it's an alias for a variable. It takes up no memory of its own. Let's pretend that's true, right? So that's what a reference is, and you make a reference by giving some other variable's name, and then the type of the reference involves the type of that original variable, and then you put an ampersand. All right, you put an ampersand. So here's how you make a reference. So here's a normal variable, int x equals 42. We understand that, right? That makes a normal, probably local variable, right? If you would like to give a new name to x, you can make a reference to it. And here's how you say that. I would like to make a reference to x, and I'll call it z, let's say. So z, I like to have it be an alias for x. Here's how you say that. Well, x was an int, so I would like to make an int reference, int ampersand. That's how you say it. Z, and then I'm going to say it's z, its name is z, and it's going to be an alias for x. All right, so here's how you read this line. So z is a reference to x. Z is an int reference to x. To the int x, all right? That's how you see it. That's how you think about it. It's kind of backwards. Z is a reference to x. kind of how I think about it. And what it did, what this line just did, is a little weird. It did that. Gave another name for the same box in memory. All right, it's not something separate, right? It's the same box. So if you said x plus plus, that would of course make x 43. But now you have another name for x. You could have said z plus plus, and for all intents and purposes now, those mean the exact same thing. You've just given two names for the same box. Okay, it's a little weird, right? So yeah, that's how it works. You give the ampersand there. That ampersand could be anywhere. I put it next to the type because it's part of the type. It's z is an int reference. But you can put it anywhere. You can put it you can spaces in between. Doesn't matter. I like to put it next to the type because I think of it as like a bigger type, a modifier to the type. Put it in the middle. Put it next to the variable's name. Doesn't matter. C++ doesn't care about white space, right? All of those mean that x is a reference to the integer y because it's an int reference, int ampersand. Is there a hand?
So for example, z doesn't get rid of the x. You just call it y.
Yeah, this is a brand new thing. You could use either name now. It's two names for the same box. Yep. So yeah, let me draw some pictures. I'll eventually give you some code for that. But let's think about this. I'll do this in a second then. So okay, let's play around with this. So int y. Let's try to figure out what's going to happen here. Int y equals 42. So that's y, right? It's a local variable, normal, no ampersands, right? So it's just a brand new variable, 42. You can do stuff with y all day long, but maybe you're like, oh, I want to call it x too. So you can say, all right, int reference x equals y. That's giving an alias to y. It's giving it a brand new name, calling it x as well. So now you can use x or y to talk about this box, okay? And so now you can say y plus plus still. Of course, y is still around. Makes it 43. You could say x plus plus, right? Because you gave a new name to that box, and now I'll make it 44. Either one works. And if you see them out, there's no real difference, right? They're both going to print 44. So you see out x, see out y. They're talking about the same box in memory. They're both going to print 44. Yeah. So that's the secret there. And let me actually show you this in code now. All right. So here is int x equals 42. And then I like to have a new name for x. I'll call it z, like I said at the start. Int reference z equals x. All right, so that's how you create one. Z is a reference to x. Okay. And now they're both talking about the same box. I can see out x. I can see out z. Those are synonyms. Those are the exact same thing, right? As far as the program is concerned. Now, x and z, they mean nothing different. X plus plus could have been z plus plus, right? They're all going to agree, right? It doesn't matter. So that is all the code, all the relevant code. And this is why you see these values. They're all going to agree, right? X and z, they're always going to print the same thing. And that was first 42, then 43, then 44. All right? So does that make sense still? They're just two different names. They're aliases, like a code word for the other, right? Code name. All right. And this might seem silly when you're in the same function. Like, why? Just remember it's called x, dude. There's no point. Or call it something simpler. Call it what you wanted at the start. The place that the references shine is in the parameters for functions. Right? That's why we're talking about this. Like, it is kind of silly to do this in the main function, I know. But we're going there. All right? We're going to functions. And I first want to teach you, like, what happens when you call a function, right? You're passing values, right? The arguments are going into the parameters. Remember that? I want to teach you, like, how that actually works, right? What happens on the stack now when we're passing values to functions, okay? I want you to think of it this way. It's a silly way, but it works. Pretend that there's a secret magical place. I'll call it the interfunction dreamland, where that's where those arguments get shoved into those parameters. All right, that's where it happens. Both of those variables are visible at once for like a split second, and rainbows appear, and that's where your functions do their things, right? To pass those arguments to the parameters. And so I'm going to give you some examples and explain what I mean by this. And hopefully that'll pave the way for what I want to do. All right, so let's have an increment function that's call by value. You don't know what that means right now, but I'll show it to you. All right. and explain it as we go. So here is a new file. I'll call it call by val and ref. There's two ways to pass parameters to functions, or pass arguments to functions and declare parameters. So let me do this. Int x equals 42, all right? And I'm going to make an increment function. I'll call it inc, call it on x, all right? And for a reason, there's going to be two kinds of the increment function. The first kind is the way that we understand right now, and that's called call by value parameter passing, all right? So I'm going to call it inc by value, but all the idea is just like it's supposed to increment x, right? So I'm going to call this function. What's it going to do? Void inc by val. It'll take a value, right? Let's call it a, for example, and it'll say a++, okay? That's its job. So here's x, 42. We're passing x into inc by val, and so like the a, right? That's the parameter. X is getting shoved into that a, yeah? That's what's happening. That is a++. Take your bets. What will be printed, right? What do you think is going to be printed if I print x now? Think in your mind, right? What is going to happen? I could doing a++, right? Like you'd think it would do something cool, right? Imagine. X is still 42 right here, all right? And that should not make that should not be confusing. And I want to draw a stack diagram for why, all right? Because these are separate places. A is local memory for inc by val. It is not part of main's local memory, all right? So let's talk about that. This is called call by value. This is the kind of functions that you know how to make. When you have parameters, you just say int, blah, blah, blah. Just the types by themselves, you're getting call by value parameter passing. And what happens is it's making copies. Copies get made. All right, and let me try and show you the interfunction dreamland now. All right, so here's main. Main had a local variable called x that held 42. Boop. And then main called inc by val. All right, it called it right there, and inc by val has an a variable. Parameters are just secret special variables. All right, inc by val. And inc by val has an a, right? It's a separate place, first of all. And then how do you get something in there, right? Just by calling the function, right? You called it with x, and x got sent in with a. But we know, like, you can only use x in main. You can only use a in inc by val, right? Because they're two separate places. For a split second, the clouds part and rainbows appear, and that's your interfunction dreamland, because somebody is initializing. It's essentially somebody's doing int a equals, right? They're making the variable, and they're setting it to that x, because that's essentially what's happening when you're calling that function. There's a magical place where both of those variables are alive at once for a split second, and you can pass values, okay? That's how a gets set to x. That's the secret, all right? And, of course, it's going to hold that 42. All right? And they're two separate places. It's just another int, because it's essentially somebody saying this, right? Int a, take this type, set it to whatever you just called it with. Int a equals that x, all right? So now they're both holding 42. It does a++, which makes it 43, but that's its a, right? It got a copy. It made a copy because it just made a brand new int variable. Does that make sense? That's what's happening. And so by the time this returns, we're back in main. It messed with a, but that was a copy. It was its local memory for inc by val. Did nothing to the x. Okay, it got copied into here. It did work on that copy, and then everybody forgot about that by the time we're down here because the stack frame went away. Okay. Any questions about that? So that's called call by value. All right, that's secretly what's going on when you have parameters that just say int, that just say double. Yeah, you have to say a. You have to use a up in this function. Yeah. All right. So usually, if you have an inc function, you want it to work like this. Like there is a way to do it, and the way is to use references. All right. This is going to solve every problem. So let me make a call by reference version of the increment function, and I'll draw for you like what happens and why it'll work. Okay. So I will call this. What have I done? I'll just copy this, I guess. I'll say inc by ref, and I will change this int a to int reference a, and that will make all the difference. Think about why. All right. And then I'll call it inc by ref on x. Yeah. I'll have to zoom out a little bit. So there's that. Let me run it. I do get 43. Ooh, x got changed by this now. Think about why. Int ampersand a equals x. Somebody's doing that in the magical interfunction dreamland. Did that make a copy? It renamed it. It renamed somebody else's memory. Cool. All right, so let's draw what's happening. Why that works. So main, again, had an x, right? Still had an x. X didn't get changed by the first call, so x is still sitting at 42, right? X is still sitting at 42 right here, right before we call it. And we say inc by ref on x, all right? Inc by ref on x. And for reasons, I'm going to draw in green everything that inc by ref owns. Its stack frame. We use a different color. So inc by ref, it's new work to be done. And then in the interfunction dreamland, right, to initialize all the parameters to the arguments, somebody says int reference a equals x. Somebody runs this exact line. Int ampersand a equals x. Okay, that's what's going on. That's how parameters get initialized. You see the difference between this line and this line? Hoo-hoo. So what is a? Is it a brand new box? It's a reference. It's an alias for something else. That's why I needed to use green here, because this is doing that. You see it? So now if you say A up in inc by ref, because that's what inc by ref knows, it's green. It only knows the green stuff. It only can see the green stuff. You are messing with this box still, which is main's box. Cool. That's super nice. And so it's going to do A++, but A is X. It's the same name. There's a different name for the same place in memory. It'll make it 43 for sure. And then inc by ref, its work is done. Last brace. It pops itself back off the stack. We're back in main. Like the A goes away, of course. There's no A anymore, but X is still there. And X got messed with. All right, so that's how you pass somebody else's stuff. You pass your own memory, right, to somebody else, and they get to use it. All right, so that's what's going on when you call getLine. That second stream parameter, that is a reference. All right, that's the secret. And so it really is messing with the stuff. And this is why. All right, and this is how those parameters are getting initialized to their arguments. And the type, you can it's like a declaration. It's just a declaration plus an initialization. And this tells you exactly why the first one made a copy, the second one did not make a copy, just reused the thing. Okay? Any questions about that? That should blow your mind, I think. I think that's really cool. Magical. So that's the reason we like references, all right? It's not so much like you do this, you're going to rename a variable within a function. No, usually reference parameters. Those are a big deal, okay? And what do they give us, right? They keep us from having to make copies. They keep us from having to make copies, first of all. So that could be something nice for us. And it also lets us touch somebody else's memory. So, yeah. That first fact, though, is kind of cool. References save memory. So let's imagine that you made a function, like in main, let's say you got a bunch of numbers from the user, and you put them all into a vector. Right? You put them all into a vector, and the user was, they had a lot of work to do, so they gave you like a size 1 million vector. Right? A bunch of files they read in, and they fed you all this data. And imagine you wanted to like sum up all the numbers that were in that 1 million sized vector, right? Or 1 billion sized vector even. Well, if you made a function that was call by value parameter passing, it would copy that entire size 1 billion vector. Yeah? And I think you can imagine like C++ has to work pretty hard to do that, right? It has to make brand new memory. It has to deal with like shifting over everything, bringing over all the values into that copy. Like that is a waste of time, right? We would like to not do that. And so if you took that vector, right, it was a parameter, vector int, if you just tacked on that little ampersand and you passed it by reference, then you did not copy that size 1 billion vector. You're just using the old one. And that saves a lot of time from having to like copy it all over too. All right, so it saves memory and time, which is nice. Take my word for it for now, at least. That is pretty nice. All right, I hope that makes a little bit of sense. So yeah, use references when you can, especially for large things, right? Because then you're not copying things over, and that saves a lot of work from having to be done. Okay, so if we are good, your turn. I have a question for you, just to make sure we understood all this. So tell me, what in the world does memory look like when I run these lines in this exact order? All right? How many separate actual boxes in memory are getting made? And which names, which aliases belong to which boxes? All right? That, I think, is a good question that we'll check and see if you understood this. So please please go to that buy clicker page. Take a minute or two to say hello to the people next to you and convince them that you are right. And yeah, try to get in one of the options. What's going to happen in memory? What will it look like? Only one of these is the right answer. Poor little air conditioning. Make sure to do attendance. I'll stop that after this question. Sunday. All right, how we doing? Ready? Bless you. Another 10 seconds to get your best guess in if you're not ready with the answer. Let's see. It's a lot of new stuff today, so it does take a while to sink in. Don't worry. But let's figure this out together. All right. 5, 4, 3, 2, 1. Done. Also done. All right. Let's see what we're thinking. Ooh, look at us. We're thinking C with a large majority. That makes me happy because I think that's the right answer. Let's see here. So, all right. What's going to go on? Let's try and draw this, right? So the first thing we do is we're going to make a variable, brand new variable called x. There's no ampersand, so that's making a brand new box, all right? All right, so it's going to be x, and it holds 42. Knowing that, you can chop off a lot of options, right? So next we say int reference y equals x. So y becomes a reference to x. It's not brand new memory. It's going to rename that box, or just give it a new second name to use. All right, so that's what happens there. And then with that in mind, like the ampersand is always giving an alias. It's giving a code name for somebody else. How many actual variables are getting made here? 1, 2. You see that? So you can immediately chop off options A and D. Immediately. It's either B or C. Those are your only options now. All right, so now z equals y. And this is interesting, right? Z is a brand new box. There's no ampersand. It's making a brand new variable z, but it's shoving into it whatever was in this box is how you read it, right? It's just another name, right? Even though y is an alias, even though y is secondly a reference, it doesn't matter. Y is the name for that box in memory, and this is how you're getting the value out. 42, it's making a copy, okay? And then, all right, in reference p equals z, so that's going to rename this box to p, or give it a second name, sorry, to p. And then int reference q equals y. Which box is that talking about? It's this box, right? The y box. And it's going to give it a third name, q. Right? So that's what's going on, and that means that C is going to be your answer. Does that make sense to us? Seems like most of us got it, so very good job. But that's the secret. If, like I gave you this on a test, a very easy way to solve this problem would be to look at all these different names and set them each to something completely different. Like, all right, I see x, let me set x to 43. Something that it wasn't before. Set y to 44, set z to 45, set p to 46, set q to 47, and then print them all out. And only the ones that are the same, those are the ones that were in the same box. Does that make sense? It's like you messed, the last one you did messed with that entire chain of those names. Yeah. That's kind of how that works. So that's one way to do it quickly and to understand it, but I hope that makes sense. All right. So that's references in a nutshell. Good for parameter passing, I would say. Not so much for just like renaming variables within a function. That's kind of weird, but useful to teach to you. All right. So are we ready for one last topic for the day? A little bit different still. All right, let's talk about multiple files now because we need this. All right, you're probably thinking that, oh man, I am putting all my work, I'm splitting them up into functions. Now all my work is being split up into functions. It's beautiful. It's easy for me to understand, but this file is just getting massive. Like I'm putting a million functions all in one file because that's all I know how to do right now. All right, let's fix that. Let's have separate files for separate ideas. All right, so let me teach you about a new extension. So we've got like CPP files, we know that. There's also a .h file, all right, and I'll teach you what that means here. All right, so that's called a header file. That's what we're about to make. That's a brand new thing. A header file, it ends in .h, or there's other options. People sometimes use .hpp or .hxx, because like the x is supposed to be like for plus plus, but you can't write a plus in a file name, so it's like they turned the plus sideways and made it an x. That's the thing. And the .cpp files are just normal C++ implementation files. That's what I'll call them. All right. Those kind of correspond to a header file. If you're going to make them, you're going to make like a foo.cpp and a foo.h together, in a sense. I'll show you what that means. So they end in .cpp. You may also see, like your book uses .cpp, so that's why we use it in this class, but you don't have to use .cpp for C++ files. You could use .cc. A lot of people use that. Google uses that, for example. .C or .cxx. I think there's even other options, but those are like the main ones. So that's something. We're just going to use .cpp in this class. And so here's the secret. Like you're going to make, the idea is like you want to make your own little library, right, for somebody else to include, okay? And that's the secret. So like you're going to make your library like this. You're going to declare all of the functions that are part of your library in the header file, in the .h thing, right? So like this is a library called foo, let's say, right? All the declarations, decals of your functions will go here. They go up there. So that's all the user needs to look at to see how to use your functions, right? They don't need to know the nitty-gritty details of how you implemented them. And then the corresponding name with the .cpp, that's your implementation file. Then you go and you implement the library. You give all the implementations for the functions that you declared. So the functions that you promised to write, all the things that you declared up here, functions defined in the header file, in the .h file, are implemented here. That's the game we play. And then when you want to use your functions, like the bar function or the foo function, in like a function, in like the main function, for example, in some other third file, main.cpp, you will include your library like this by including the header file, number sign include, and then you give the name of your library not between those angle brackets, but between double quotes, all right? With double quotes, those angle brackets are reserved for system level libraries, okay? So you just give its name with between double quotes, it'll find it, and that's kind of how it works. You compile, the way that you compile, for a reason I'll show you soon, is you don't have to use the header file when you're compiling, but you have to give every implementation, like, all right, there's some code here and there's some code here. So I'm giving to G++ both the library implementation file, foo.cpp, as well as the main.cpp file with the main function. That's how you're going to compile it, all right? You got to give them both, but not the header file, all right, for a reason I'll show you soon. And that's where you include your things. Customarily, in your implementation file, you also include the header file. All right, just get in the habit of doing that. It's technically not necessary here, right? But I'll show you why soon, one day. But that's kind of how it starts. And yeah, I think that's all that I wanted to say with words. Are there any questions before we go to code? All right. That's how it works. That's how we can split up our ideas into separate little libraries. So you can include multiple of them. Foo.h, bar.h. Right? So let's take what we did like last time and convert it to a library, because we made a bunch of different functions, right? We did like the sum of the squares stuff. Let's split it up into 3 separate things. Let's copy that file in, first of all. What do I want to call this? In fact, I will make a new folder for all of that, because there's a bunch of files. I'll make a brand new folder. Make do sum of squares. That's where my library is all going to live, and all the stuff I'm about to do. Sum of squares. And let me copy in lecture 11's sum of squares.cpp to here now. All right, so there it is. There's the old file that we made last time with everything in it. All right, and then I go into that folder here, So here's the file. We've got the declarations of our functions, right? We're going to package this up into a library now. We've got a main function that uses our functions that we made, sum of squares. And then we have all those implementations down here, right? This is kind of long and definitely long-winded. So let's split it up. Let's take all these things that we made before and we'll split it on up into a library. I'll make 3 files. Main.cpp, that will just hold the main function. We'll use our sum of squares library there. Main.cpp, all right? And then sum of squares.h will declare all of those functions in my library, these guys, the declarations of those. That's where I'll put those. Of sum squares from 1, 2, which I don't want to write out. And then in the corresponding CPP file with the same name, that's the game we play, we're going to implement them all. Put all the implementations there, all right? So that will have the implementations of all those guys, all right? So that's the setup. Let's do it now. So I'm going to make, I already have sum of squares.cpp, I just got to get most of this stuff out of here, okay? So let's do the header file first, sum of squares.h. That will contain the declarations of all these functions, all right? So let's go here. Let's delete from there, add to here. All right, so that's the header file. Just the declarations of the things in our library that we promised to give to our users. There's that one. And then we also wanted to make a main.cpp that had our main function and used the library. Okay, so that's all this, I guess. Delete that, make a new file called main.cpp, put it there. And I'll make it right in a second. And then the rest, this was sum of squares.cpp, that had the implementations of everything. Okay, so I've got that. Customarily, in your header file, you want to include, or sorry, in your implementation file, you include your header file, even though technically not necessary here. It's just a good habit to get into. It's not going to hurt you. Include it. Where we do need to include it is when we want access to using these functions, right? We want access to them in main for sure. Main is very confused right now. It's like, what are you talking about? I don't know what this thing is. We must include our library to gain access to it, okay? So we'll say include, and with just quotes, it's going to be sum of squares.h, okay? And then suddenly it's happy. It understands, okay, yes, I know where that function is now. We're good. I know what it means for you to call this, okay? And so here's the main function file. Here is the header file. Here is the implementation file that implements all these bad boys. All right, they're all working together. And if I want to compile and run this now, I have to give just the implementation files, just the .cpp ones, the ones with real code. All right, so I'm going to say G++, I will give main.cpp as well as sum of squares.cpp. Take them both, package them together, because like it needs all the code from everywhere, and call it something, let's just call it main. All right, and it's happy. It runs, and I don't know, 42. It did its thing. All right, so that's how that works. And so I use multiple files to separate my concerns. All right, and so it's much easier to read this main.cpp file. It's much easier, just like, okay, I'm going to use this library. What does that library include? Just go look at the header file. You don't really care about the implementation if you're just going to use the thing. Yeah? That's kind of the point. But yeah, that's what's going on. Does that make enough sense so far? No, because that is that file. This is sum of squares.h. There's no need to include itself. Yeah, it knows who it is. For now, at least. Yeah, that is a good question, though. I'm going to mess up. You can mess up in a second by doing that, actually. So that's a good segue. Let me teach you what include means now. When you say #include, it's really just going and looking for a file somewhere. Like this is a file name, right? This is a file name. IOStream is just a secret file name in a special place, right, from the library. So when you #include something, first of all, it's a file, right? It's always a file. It's a secret file. What happens is wherever you said #include that thing, it just copied and pasted that entire file right there. Right? It gets copied and pasted. And pasted. Right? That is the secret, and that's honestly why you don't have to give anything to G++. Like it's already getting copied and pasted. Like sum of squares.h, you say include that. All it does, legitimately, what happens when you say that as it's being compiled, it takes that file's contents, shoves them right there, and that's what it really compiles. Okay, that's the secret. And that's how it knows, like, it's what we did before. We declared everything above main. That's what it's doing for you, essentially. That's pretty cool. All right, so that's what's happening there. And yeah, it's getting copied and pasted into that file. All right. Because of that, that's one reason why you might want to include it in your library, because like maybe you say something that you want it declared and like you implement things out of order and they call each other or something. Like that's the reason why you put this up here. Not really useful here because none of these call each other. Not a big deal though. Or they do, but like it's at the end. So if I rearrange those, you'd need this still. But yeah, you could run into trouble now with that number sign include. All right. And here is one way, like it'll be much more subtle than this when it happens to you, but let me show you what happens. You can get into infinite loops of inclusion, surprisingly. Okay, so here's what you could do. This could happen to you one day. I promise it won't be as obvious as this, but it's possible to have libraries that like use each other. One library is implemented, uses this library stuff, and this library, as it's implemented, it also uses some of the other library stuff. So they're kind of including each other, all right? So you might end up, when you do that, essentially doing this, sum of squares.h. You're including, somehow, through some weird chain of events, you might end up, with enough copying and pasting, having something like this in the actual sum of squares.h file. Okay? And so what's it going to do, right? It's going to, all right, I know what it means to include something. Copy, paste, delete the original one, and then you have two of these, and you still have the include. You see that? So, and then it'll do it again. Paste, still have the include. I got like 3 of them or something. So what happens when you do this is you get caught in an infinite inclusion loop, and G++ is very unhappy. From the same file, it's doing all this, and yeah, it just keeps on including itself. You've done, like, you're including itself 200 times, and now I give up. Luckily, it gives up, right? So that is an issue you may run into one day just by using multiple libraries that use each other. Okay, it won't be as obvious as this. But if you want to prevent this, well, let me show you the hard way, because eventually you might learn in like the book the easy way to do this. But I'll show you the hard way so that you know it each way, always. All right? So here's how you fix it. Here's one way to fix it. You say these 3 things. You say if ndef some name that involves the name of the file, like all caps usually. You change the dot to an underscore. If ndef foo h, define foo h, and then ndef. What this is a compiler level if statement, if that makes any sense at all. You can just memorize this. This is one of the few things you can memorize. It doesn't really matter. But what it's doing is it's saying, all right, I'm going to make a special compiler level variable called foo h. If that is not defined currently, define it to be emptiness. It's like you could define it to be 42 if you wanted, but we'll just define it to be emptiness. As long as it exists, we're happy. And then you put your code, the stuff that you want to include in the actual file, and then you say endif. That's like the end curly brace for the compiler level if statement. And what that does is it tracks this little variable's name. Like if this already exists, that means this file has already been included, right? Because like it was false, we went to here, we defined foo.h or foo.h, and then we included the file actually. If I ever get here and I see that it already is defined, I will skip over all this as like the body of the if essentially. And that's how it won't keep including things. So like this wraps around your entire file and it makes it happy. Okay, so the compile time variable that keeps track whether that was included or not. All right, so that's the secret. You can even keep this in the file if you do that. It'll just only include it once. It's like, all right, yeah, I've already done this once. I don't need to do it again. So this is how you say it. You say if ndef, and you give a name of. It usually involves the name of the file, and it's like you're shouting all caps. So sum of squares underscore h, because you can't use a dot in a variable name, right? If it's not defined, define it. Define it to be emptiness. Then you put the actual file that you want to include, and then you say endif, right? And that just like fixes everything. Bam. Even though this happens, it's going to get copied and pasted. It'll copy in all this to right here. Boop. See it? But then it's going to be like, oh yeah, this is already defined. It was defined up here. So like all this, boop. It's just emptiness. It doesn't run the body. And it's like, we're back to normal. Everything's happy. That's kind of why that works. All right, so yeah, it works now, even with the mistake, and everybody's happy. Right? So that's the library. That is the secret of all that. And you can make as many of these as you want. Just package away separate ideas in separate files that you don't have to look at unless you need to. All right? Any questions about any of that? That's a lot of stuff. I know. We got there. We did it. All right. If we're happy, I just want to keep reviewing all this. Like, there's a lot of new information today, I know. So let me have an extended example for the day. I'll almost get at, like, I'm going to make a counter idea. I'll make a counter library. It's almost the thing I made for you at the start of the semester, but not quite. All right. We'll use functions, though. All right. We're just going to practice these things. So we're going to make a counting device as a library, essentially. All right. And so let's plan out, like, what do we want in our counter library? Counter.h. What are we going to put there? Okay. We need, like, if we're going to model this thing like that's a counter, well, we need to store a count secretly somewhere. Like that's the count on the window of the little machine. Yeah. So we need that. We need to store the counter's count. We'll put that for a reason as a global variable in the implementation file. All right. We could have started out as 0 normally, just like int count equals 0, but for a reason that will come up later, let's make an initialization function for all of our memory for this library. All right, for this library. We'll initialize it to be 0 with a initialize function. All right. We'll just call it once before we ever use the library. That'll be the game that we play. That'll be our promise. That'll set count to 0. And then we need, an initialization function. That's a hard thing to say fast. In our library, we need that. Then we're going to want a function to click the little button, right? We want an increment function. That will take our count variable and increase it by 1. You can increment it a couple times. We should also have a decrement function that takes our counter variable, decrements it. We can have a reset function that resets the count to 0. We could have used the init function for that, but we're going to try and separate those two ideas, initialization from, like, if we ever want to do anything else to it. So, like, we'll have a reset function, and then we also want to be able to, like, look at the window. And so we want to do that with functions. It's the best way. So we're going to make, like, a get count function to go look at the count for us and give it back to the user, because they're not going to be able to see it. We're going to put it in the CPP file. They don't even know it exists, right? That's the secret. We're hiding it from them. So they can't mess with it. They can only go through our functions to mess with it. All right. So with that in mind, here's what the library will hold: an initialization function, increment function, a decrement function, a reset function, and a get count function. All right. And that's what the user will use if they want to have a little counter in their program. All right. It'll package around all those ideas. All right. So let's see what I want to do here. Dun, dun, dun. Dun, dun. We are absolutely going to split this up into multiple files, and so let me make a new folder for all this. I'll call it counter folder. So let's go work inside of that. Boop. There we go. Let's call this counter.h. Let's do that first. All right. So remember, to prevent from infinite inclusion, you would like to use header file. These are called header file guards. All right, they keep you from doing weird things. And then here are all these. Declare that they exist. What are their types? So init counter is just void. Increment, you just call it, messes with the count, void. Same with decrement. Reset even is void. Get count is going to be your one function that gives back something. It'll return the actual count value. All right. So those are those. And then let's pretend we have this now. Let's go to like a main.cdp and let's include our library. Counter.h. Let me show that to you. There it is. So here's kind of how I want to use my library. We must always initialize our counter. All right, we're going to remember to do that. Init counter. Before we do anything, we got to do that. And then let's increment our counter 3 times. Ink. So now it's 3. Let's decrement it once. You could do that. And now let's look at the count window. Let's be like, see how get count. Right? So this is just a very complicated program that's going to eventually print 2. Yes? All right. And that's how I want to use these things. So now let's go and let's implement all these functions in the implementation file. So make a counter.cdp file. Customarily, we will include our header file. Again, not super necessary, but might as well get in the habit of doing it. It'll only help us in the end. And then let's implement all these bad boys. So the secret is we are going to put a global variable in this file. All right, we'll call it int count. That's our global variable, and that's what all these functions are going to mess with. All right, they're all going to mess with this global variable. And notice how not part of the header file. It's not part of the header file. So this main.cpp, which is including the header file, it has no clue about our secret count variable. They can't even touch it. They don't even get to use its name. It's not alive at the same time. So they don't get to see it. It's just for us. We're hiding it from them. All right. So they can't do something weird, but like saying the count equals 42 or something. They have to go through our functions to mess with it. That's why we do that. We're hiding it from the user. All right. Who's using our library. But of course, we, the implementers, get to see it all. So all right, how does init counter work? It should initialize the count. Almost said a word. That is part of classes and not functions. We're going to initialize it to 0. All right, so that's what that should do. Whenever you call init counter, take our count global variable, set it to 0. All right, and then inc and dec, and they're all going to mess with count. All the other ones. Okay, so like inc should be count plus plus. Does that kind of make sense? Is that a question? Yeah. I put it in the CPP file. I put it in counter.cpp, not counter.h, because main here, it knows about IOStream stuff, and it knows about counter.h stuff. It has no clue about counter.cpp stuff. We're not including that file. Okay? So it doesn't get to see any of this. That's the secret. So main only knows about the stuff that we tell it to know about. Yeah. So back to the header file. So, all right, mess with that. Decrement, count minus minus. Reset, set count to 0. You could potentially like make a reset function like give me a count that you want to reset it to, a new count or something, and you can change it to that. Like that's a thing that you could do, but we're just going to make it 0 for fun. And then get count, finally, that's the only way the user gets to know about this thing, right? Because we're hiding it from them. They only get to use all this stuff that we showed them. So we'll say count. This is how we will ever so nicely let them see the value, right? So that's going to be our library implementation. There's the header file, and that should do it. So let's go over here. What have I just done? Oh gosh. You need to be saved. You need to go here. Again, try to show them all to you at once. Cool. So yeah, here is main.cpp. That's including our library and using it. Here's the header file that's declaring all these functions of our library. And here's the implementation file that actually goes off and implements all those things and also has the memory that we're going to use for our counter. Okay. So to compile, we give all of the implementation files, and I'll call the final executable main again, I guess. And wow, we got a program that prints too. It's beautiful. So yeah, this is a great one to study, I think. Are there any questions about this? How it's working? We kind of see it, kind of visualize it. Try to draw a stack diagram. Like it's useful stuff to practice these things. Let's see, what else do I want to do? If we're good with that, I think we have time. And honestly, it's useful for you to try this too. So here, let me give you all the code right now. I'll give you some time to do this, and I'll give you a head start at least. So if you go to any other lectures code from class folder, right, you will now see lecture 12. Oops. And you will see all my files in this counter folder. And you will also have, you can see the counter. I'd like you to make a test right now, to make it in the main file. We did some testing code last time, right? That was in lecture 11's testing.cpp probably, yeah. We use assert true, all right? So what I'd like you to do is take this assert true, bring it over here. Maybe I'll just give you this code in a second. Include the string library. And what I want you to do, instead of all these things, is I'd like you to make a test. A test that uses assert true to kind of test this idea, all right? If I run a init counter, inc 3 times, dec once, and then get count, I better get back 2 from that last call to get count. All right, that's the test I'd like you to write here using this assert true. And here, if you refresh the page, let me just let me give you this version of the code. If you refresh my main.cpp file, you'll get to see that assert true now. Taking this, using that in the way that we did before, try to make a test that checks exactly this with assert true. All right, see if you can remember everything. I'll give you a few minutes head start, help each other, and then I'll show you how I might think about it. Head start. So essentially, you're just going to take all the code that I did, and then instead of printing something, right, you're going to check something. Okay, was that handy? Also, almost put together for the class page. Oh yeah. Oh, okay. So yeah, you guys gotta be using my code from last week. Go to the canvas. Yeah, you've never used this before. This is like the greatest thing ever. I've given you every piece of code I've ever written for you. I'll give you a couple more minutes head start. Remember, to compile, you're going to use both the CPP files together. All right, that's my timer. So keep trying if you'd like. You can look away. I'll eventually give you the answer when you refresh the page, after class at least. But here's how I want to think about this. All right. So running these things in that order should do this for me. And so I have to run them still somewhere. But maybe not in main. Let's make a brand new function called like test counter. All right. I'll put that up here. Void test counter. And that's where I'll do all these things. Run all these in that exact order, actually. And then instead of printing the count, right, we want to check, hey, was that count actually 2? Does that kind of make sense? So this is going to return something. Don't have to print it. Just got to use it. I would like to assert, right, that this is 2. Yeah, with my assert true. I would like to assert true that whatever I see here, whatever I get back right now after doing all this stuff, all this hard work, better give me 2. That is your test. Does that kind of make sense? That's how you do it. And then you give it some name. Counter test. And you should probably make more because I have not even tried to run that reset function yet. So let's make sure that works for sure if we can. All right. So that's going to be how that works. And to compile it again, we're going to give. How about I do this? We're going to give all the implementation files to G++, and then you call it whatever you want still. All right. And it passes. Yay. So that, I think, is a good last example to review testing, because testing is very important. Okay? So yeah, I will eventually give you my version of this code, but keep working if you like on yours. Are there any questions about this? All right, so that is where I want to stop for the day. Let me just confirm that I have nothing left to give to you. Yeah, no new labs this week. Just keep working on the ones that are already out.